All right, well, I made the maybe ill-advised decision to speak to you about something that I'm really excited about, which is brand new and unpublished, and I've never given a talk about it before, because this is a workshop and I want to share sort of a breaking, exciting idea. So rather than being a kind of broad overview talk about the many things my lab is doing, which Pascal just hit out of the park, so I wouldn't want to have to compete with that. I'm instead going to dive deep in one thing, which has been sort of a white whale for me. I'm really troubled by a kind of philosophical question about algorithm design, and I feel like we have something quantitative and crisp to say about it that could really make a difference to the field. So we're going to spend some time on some details, but I think that the overall message of this talk is something that I'm really excited about. Let me say that this talk describes primarily the work of my wonder student, Devon Graham, who's here with us, and maybe some of you will meet him afterwards. It's also a collaboration with Tim Roughgarden at Columbia. So the talk is called, what does it mean to prefer the fastest algorithm? And that might seem like a ridiculous thing to say. So I want to begin by explaining to you why asking that question is a sensible thing to do. So I want to begin by asking, which algorithm should you prefer if you have a family of algorithms that always return the right answer, but that vary in their runtimes, like a set of stat solvers? So, so I don't want to think at all about algorithms that you get better and better solutions the longer you run them. I want to just really think about algorithms that always do the right thing, but sometimes they take a long time to run, sometimes they take a short time to run, maybe they're randomized. So a lot of existing work, particularly including maybe some work of my own, but certainly a lot, I think the most generic thing you might say in the field is that the best algorithm is the one with the best average runtime. So we should try to find an algorithm. If all we care about is runtime, we should try to minimize average runtime. So I want to argue to you at the outset here that as common as it is for us to say that, we don't really believe it. And I want to illustrate that with an example. So imagine that you had a choice between two algorithms. Algorithm A1, and you have 100 instances from a distribution, or you have a distribution that can generate arbitrary instances and you sample 100 things. Algorithm A1 solves 99 of these instances in 1 second. And you run it for 10 days, and after 10 days, you're frustrated about waiting so long, so you stop the run, and all you know about the 100th instance is that you didn't solve it within that amount of time. You know the algorithm is going to terminate, so you know at some point it would solve it, but it didn't solve it within 10 days. Now, algorithm A2 doesn't solve any of the instances in the first 10 days. Again, you stop it, you know that it's going to terminate within some time, but it didn't solve any of them. Now, the first problem I want to point out to you is that average runtimes are completely unconstrained in this case. I don't know that algorithm A1 has a better average runtime than A2, because it might be that on the slightly more than 10 days, algorithm 2 finishes for everything. And algorithm A1 on that 100th instance takes an absurdly long amount of time that dominates the average. And so in the end, algorithm A1's average is worse than algorithm A2's average. So, so does that mean that I don't know enough to have a preference between the algorithms? Now, secondly, what if what I said before wasn't true? What if both algorithms actually turn out to contain a bug and the long runs never terminate at all? Now both averages are infinite. Does that mean that I ought to be indifferent between algorithm A1 and A2? I claim both of those suppositions are absurd. I claim that most of the time we face algorithms that can't solve every problem, particularly when we're working on NP-complete optimization problems. We have to live with cases where we can't solve absolutely every instance that we see in the time that we have. And so we have to trade off performance in the common case against occasional failures. And we have to face much harder comparisons than this one. We're going to eventually want a theory that can do more than only to describe this kind of easy case. This seems like a pretty obvious case where I think everyone in this Zoom call would prefer algorithm A1 to algorithm A2. So I want to think about why that is and how we can formalize our preferences in a way that doesn't tell us that this becomes absurd, because we can see average as much as we use it. It's not a really good proxy for what we appear to care about. Another thing that you can do that is unproblematic is to say, what I really care about is just how many problems solved within my cap time. So that works, but it makes my cap time really important. I have to really believe that 10 days was the right amount of time, and that solving the problem in 1 second or solving the problem in 10 days is exactly the same to me. And that's fine as long as that's really what I believe, but otherwise, this doesn't express that trade-off. If you want to start getting into that trade-off, you can then start thinking about penalizing capped runs. So another thing you can do is to say, let me just imagine that when I cap a run, it completed at the cap time. Then I have something that I can take the average over, but it might not be preserved. As I change the cap time, I can actually have inversions in my preferences. And to try to deal with that problem of inversions, there's something that Holger, who's Frank Hutter, and I made up in an early algorithm configuration paper that we called penalized average runtime, or PAR-K, that said, let me just make up some constant K that says, when I cap something, I'm going to say that it cost me K times the cap time. So I'm going to try to separate it from the cap time. Maybe that's okay as a heuristic, but you can see it's going to have the same problems, that I can have these funny inversions. It doesn't really, it's not really a principled way of dealing with this problem. And in fact, we can come up with crazy algorithms like the St. Petersburg algorithm, which is a sort of algorithmic version of the St. Petersburg paradox that says, if I have an algorithm that finishes in 2 seconds half the time, in 4 seconds a quarter of the time, 8 seconds an eighth of the time, then I have an average runtime that's infinite. And I can basically choose its score by choosing its cap time. So I can give it any score I like by setting the cap time in a different place. And that seems to show that these particular ways of coming up with scores by looking at the fractions of problems solved or these various PAR variants really give us a tremendous amount of power in what scores we're going to give things by the way we set this cap time parameter, which sometimes we maybe don't have a really principled way of thinking about how to set. So the reason that I care about this, and I think the reason that this problem is more than a philosophical curiosity, but something that this workshop should really care about, is that we're increasingly in AI coming to think about algorithm designs as a hypothesis space that we want to optimize over, rather than a sort of handmade thing that we just reason about. So, in machine learning back in the 90s, people used to think about this classical approach where you would make features based on expert insight. You would tune a model family by hand. Maybe you'd go to NeurIPS and you would figure out what the fanciest version of SVMs was that year. And then you'd manually tune some hyperparameters to come up with your best model. And as we all know, we've moved to this end-to-end kind of world where we work with incredibly highly parameterized models, where we use very much less expert knowledge to identify kind of at most invariances and biases. These models are deep in the sense that they have many layers of nodes or parameters, each of which depend on the last. And we solve the problem of this enormous parameterization in two ways. We use tremendous amounts of data to avoid overfitting, and we just brute force the optimization. We do enormous amounts of search instead of this clever human design. So I think our field is coming to realize that when we think about discrete optimization, we need to make the same move. So back in the 90s, or even the mid 2000s, when people thought about discrete optimization, we did something that I think looked a lot like the classical approach in machine learning, where an expert designed a heuristic algorithm and then iteratively did small experiments to tweak the design and refine their expert opinion about how the heuristic should work. And I think now we're doing what I call learning in the space of algorithm designs, where we start with very highly parameterized algorithms that maybe still express points in some heuristic space, but this space might be some enormous combinatorial space that the expert doesn't really understand. And these designs are deep in the sense that there are many different layers of parameters, each of which might conditionally depend on the previous. And we solve the problem in the same way we did before. So we have lots of data to characterize the distribution that we want good performance on. And we just brute force the search over algorithm designs rather than using some kind of deep human insight into how each respective algorithm in the design space performs. So far, so good. There's more than one kind of paradigm for this learning in the space of algorithm designs, but something close to my heart and that we've heard about already at this workshop today is algorithm configuration. So basically, in this kind of view of the world, you have a target algorithm that solves problem instances, which is parameterized. And you have this kind of meta algorithm called a configurator that calls the target algorithm with different parameter settings, observes its performance, and then makes decisions about how to kind of do automated experiment design, sort of repeatedly make these calls in order to optimize solution cost over time. And the critical thing about this picture is that we need to get the solution cost right if we want this whole thing to work. The configurator is just sort of parameterized by the solution cost, but the solution cost is like the thing like average runtime. You know, if you know the work from my group in the past called Structured Procrastination, the sequence of papers by DeepMind and my group that have built on that, it all says, you know, how would you do theoretically well-grounded algorithm configuration in the case where what you really care about is optimizing for average runtime? Well, if you don't believe that you really should be optimizing for average runtime, then that theory only gets you so far. So what would it look like to take more seriously the question of what the solution cost really ought to be, so that when we do this kind of open-ended design, we can do it with the right objective function? You know, as we all know in optimization, changing the objective function can make a pretty big difference to the solution. And so that's what this talk is going to be about. I'm not going to tell you about how we should actually do algorithm configuration, because this is really just a talk about objective functions. But I want to think about, you know, how we should think about how we prefer which algorithm to you know, out of a set of algorithms, how we should decide which one is the fastest when presented with a runtime distribution and when faced with the inevitability of capping some runs. Okay, so now I'm going to get a bit more technical and talk through how that is actually going to work. So I want to think about a world where I have some set of algorithms, script A, and I'm going to overload notation. So each algorithm A in this set of algorithms is a distribution over possible runtimes of the corresponding algorithm. So I'm going to identify an algorithm with a distribution over its runtime. That's the only thing I really care about here, is distributions. And notice that I'm sweeping under the rug randomization in the algorithm. That's just going to be part of inducing this distribution, and also kind of randomization in the generating process over instances. That's another sort of source of randomness. And I'm just folding those things together to say this potentially randomized algorithm in the world that it lives in induces a distribution over runtimes. And then I just want to say, presented with a set of distributions over runtimes, I want to think about how happy they each make me so that I can make decisions. So notationally, I'm going to use a little t sub a to denote a runtime sampled from A. And these runtimes are, of course, going to always be non-negative. I'm going to allow them to be infinite. And I'm going to use Dirichlet delta notation to speak about the deterministic case. So I'll say the algorithm's runtime distribution is equal to delta t in the deterministic case where runs always take t. So just notationally, you'll see these deltas a lot. That's what I mean. That means deterministically always t. And now I talked about cap times. You might imagine that I just know that my cap time is 10 days or something like that, but it's going to play an important role in what follows, that the cap times might also be drawn from a distribution. I might be uncertain about exactly how much time I have to do my runs. So I'm just going to allow that. Of course, I could always, the deterministic case is a special case of the randomized case, but I'll say that capital K is a distribution over possible cap times. Kappa is a cap time that's sampled from this distribution, and I can use again this delta notation if I want to say that the cap time is fixed and known. So the goal of this talk then is to find some score function that goes from algorithm runtime distributions to real numbers that corresponds to my preferences over algorithms. So I want to say, find me this real valued score function that I can apply one by one. Yeah, I can think of kind of as a loss function that I can use in my machine learning kind of setup to say, let me look at how much loss I get from this algorithm, and doing better in terms of loss is always going to correspond to picking an algorithm that I really do like better. So algorithm one is weakly preferred to algorithm 2, that's what this squiggly greater than symbol means, if and only if my score for algorithm 1 is greater than or equal to my score for algorithm 2. So that's going to be my mission statement here, trying to come up with some score like that. And notice that I told you about cap time distributions. I didn't say anything about cap time distributions, so I'm going to have to fix that. So what I really want to say is I want some score function parameterized by kappa, which is going to speak about my preferences in the case where the runtime distribution is parameterized by kappa. So I'm going to subscript the relation by kappa to say, to recognize that my preference between algorithms might depend on kappa. The algorithm that I like best when I know that I have only 1 second might be different than the algorithm I like best when I know that I have a day, because maybe algorithm 2 takes 2 seconds all the time, and if all I have is 1 second, I have to pick a different algorithm. So I have to recognize my preferences are going to depend on what I know about kappa, and so I'm going to parameterize both the score function and the relation by kappa to do that. So I'm going to take here an axiomatic approach. I'm going to reason from observations about preferences in easily understood scenarios. I'm going to argue that there are things that must be true about my preferences just based on what I understand about algorithms and about being an algorithm designer. And then I'm going to set up these axioms in such a way that we can do a bunch of math and derive a general rule that tells me what my preferences have to be in all scenarios. And we're going to follow in the footsteps of von Neumann and Morgenstern, who back in the 40s used this kind of approach to axiomatize expected utility, and we laid one of the key foundations for microeconomic theory. So we're going to mimic their proof as much as we can, but our setting where we have these cap times and where outcomes are probability distributions themselves is sufficiently different from theirs that we have to make some tweaks, but we're going to sort of try to stay in the tracks that they laid as much as we can. We also benefit from the fact that we're speaking about a less general setting than they are, so we can introduce some additional runtime specific axioms that allow us to constrain the utility functions further. So let me tell you about these axioms. All of this gets pretty technical. I'm going to have to keep it, go through this kind of quickly, but you can look at the slides later if you want to read the subscripts really closely and understand the details. So the first axiom, transitivity, says my preferences are acyclic. So if I like algorithm A1 better than A2, and if I like algorithm A2 better than A3, both in the context of some cap time distribution K, I'll stop saying that out loud, but that's always going to be there, then it's also the case that I must like algorithm A1 better than A3. I can't have a funny cyclic preference in my algorithms. I'm going to define a mixing operation that says, remember algorithms are just runtime distributions, so I can kind of create new synthetic algorithms by composing runtime distributions together. I can say, imagine I had 2 algorithms, A1 and A2. Well, I can make up a new kind of synthetic algorithm that says with probability P, I run algorithm A1, and with probability 1 minus P, I run algorithm A2. That gives me a new runtime distribution, which is this convex combination of the first 2 runtime distributions. And the thing to notice is this itself is just a runtime distribution. This flattens out, it becomes another algorithm. So I'm going to call that mixing. And I'm going to use this notation that you can see here. So monotonicity is an axiom about mixing. It says, if I like algorithm 1 better than algorithm 2, then for any probabilities P and Q, if and only if P is greater than Q, then I like getting algorithm A1 with probability P better than getting algorithm A1 with probability Q. So it says, if A1 is better than A2, give me more of A1. As I turn up the dial on how much of A1 I'm getting in an A1, A2 mixture, I get happier and happier. And continuity says, I can always find some indifference point when I have a sequence of 3 preferences. So if I like A1 better than A2, better than A3 all weekly, then there exists some probability that I can use to create a mixture between A1 and A3, my 2 kind of extremal algorithms, that'll make me indifferent with the one in the middle. So if I have 2 things that in my preferences bracket, at least weekly, something in the middle, then I can make a mixture between the bad thing and the good thing that drives me to indifference with the thing in the middle. And lastly, and most complicatedly, I have an axiom called substitutability. And here I have to define something called compounding. So imagine that I have a collection of distributions MT kappa. And these distributions can be absolutely anything, but they're parameterized by T and kappa. So what does that mean? It just means you give me a T and a kappa, I'll give you back a distribution. It can be anything, but it just has to be a function of T and kappa that works for any T and any kappa. So imagine I have some algorithm A and I have some runtime distribution kappa, cap time distribution kappa. Imagine then that I was to sample some T from A, sample some kappa from kappa, and then return to you whichever distribution MT of kappa gives you. If I was to do that, that whole sampling procedure and create that as a mixture, where with the probability corresponding to getting exactly that T from A and that kappa from kappa, I get the 1M, and I do this for all the different M's in the whole collection. This gives me some huge mixture. I'm going to call that a compound distribution. So this is just a way of kind of inducing a distribution by sampling. And substitutability is a way of saying, basically, if I'm indifferent between sure things and distributions, deterministic algorithms that always take runtime delta T, then I can kind of lift this up to distributions over algorithms A. So it says, if for every T in kappa, I'm indifferent in the case of facing deterministic cap time kappa between obtaining runtime T with certainty and sampling a runtime from some given distribution MT kappa. And again, if this is true for every T in kappa, then I'm also indifferent in the case of the cap time sampled from K between the runtime distribution of algorithm A, which is now a distribution, not a sure thing, and the runtime distribution corresponding to sampling T from A and kappa from K, and then sampling a runtime from M, this compounded distribution. So what this is saying is if I'm indifferent pairwise between delta T and MT kappa in the deterministic delta kappa case, if all of those things are indifferent, and then I just kind of go from this X post case to an X ante case, where I've got the whole distribution A and the whole cap time distribution K, and I'm just kind of averaging over all these things that I'm indifferent about, then I remain indifferent. The fact that I'm doing this averaging over things that I'm indifferent about doesn't break my indifference. So this is our most complicated axiom, and apologies if that went too fast. It plays mathematically a pretty similar role to an axiom that Van Neumann and Morgenstern use in their construction that they call substitutability, or actually that has subsequently been called substitutability. But mathematically it's different because we need to reason about base outcomes that correspond to distributions from which we can sample. Our preference relation is actually defined with respect to a cap time distribution. So we're actually relating preferences under one preference relation to preferences under another preference relation. Notice all of our other axioms had the same squiggly equals symbol, but here I'm relating delta K to K. Fine, so anyway, that's our substitutability axiom. If I take these four axioms together, turns out I'm going to show that they imply the existence of a utility function. They imply that I must have some kind of utility over algorithm runs. There are two more axioms that I want to assert to you that are going to further constrain this utility function and make it make more sense in the case of runtime. So the first we call eagerness, and basically the intuition here is that I like fast runs at least as well as I like slow runs. I'm never happier by waiting longer for a run to complete. So this just says if I think about two runtimes, T and T prime, and I have some algorithm's runtime that is strict, its entire support is contained between T and T prime, then I like deterministic algorithm that takes T at least as well as I like this, this randomized algorithm A, at least as much as I like deterministically taking T prime. The T and T prime just bracket the runtime distribution A and its PDF. And my last axiom, relevance, just says, I'm running this algorithm for a reason. I actually want the answer. I'm not indifferent between solving my problem and not solving my problem. That's why I'm doing this whole thing. So this is my only axiom about strict preference. It says the deterministic algorithm that takes time T is strictly preferred under deterministic cap time kappa to the deterministic algorithm that takes time T prime whenever T is strictly less than kappa is weakly less than t prime. So what I'm implicitly saying here is if you take kappa, you don't get the answer. You don't just eke it out. I'm saying when you take kappa, you fail to solve the problem. That's the kind of boundary case where you don't solve it. And so you're happier to solve your algorithm than you are to not solve your algorithm. Now, here is the kind of mathematical punchline. If our preferences follow these 6 axioms, then for any runtime distributions that you might have, and for any cap time distribution you might have, there has to exist some function u that maps from pairs of runtimes to the 0-1 interval, such that this does exactly what I wanted in my score function. It sort of behaves like a score function. So my preferences between A1 and A2 under runtime distribution kappa are exactly the expected values of this function u under the runtime distribution and the cap time distribution. So I can look at this function u, I can take its expectations under the runtime distributions and under the cap time distribution, and that's going to tell me exactly which algorithm I prefer. And as I learn different things about the algorithm, that just changes with the expectation I have to take. As I learn different things, as I might change the cap time, that again just changes an expectation. This u function can just be left alone. And not only that, but I can reason some things about the shape that this u has to have. With a runtime 0 for every kappa, u is going to be equal to 1. Remember, I told you this function is on the interval 0, 1. It's then going to be weakly monotone decreasing. It's allowed to plateau, but it's never allowed to rise. It has to remain strictly positive for all t less than the cap time, and it has to become 0 exactly at the cap time and then remain 0. And it's allowed to discontinuously fall to 0. So I must have some utility function that looks like this. The assumption about the bounded interval being 0, 1 is not important. That's why the statement is existential. It turns out I can do an analogous thing on any bounded interval that you like by taking affine transforms of the u that I just told you, and then you get an if and only if result. I've left that out to keep the notation simple. So I don't have time to go through the proof here. I'll just kind of put the proof sketch up. But the first part about the existence of u basically adapts von Neumann and Morgenstern's proof to our setting. And the key idea is to find probabilities p, t kappa that make us indifferent between the best and worst possible outcomes. So the best possible outcome is solving a problem at time 0. And the worst possible outcome is timing out at kappa, because I know that I'm indifferent between all runs that take longer than kappa because they all just time out. And so kind of a key result that follows from continuity is that for every non-negative t in kappa, there exists some such probability that's going to make me indifferent between some mixture between getting runtime of 0 and capping out. And then these probabilities p are going to turn out to be my utilities. I'm going to be able to construct a utility function on this interval 0, 1, where these probabilities are going to correspond exactly to my utilities. And the rest of this part of the proof corresponds to establishing that these probabilities really must align with my preferences by applying substitutability, monotonicity, and transitivity. So I'm skipping over that part because, in the interest of time, and because it has the least to say about, it's similar to what von Neumann and Morgenstern do. The second part speaks about the structure of u. I guess, again, each of these pieces follows by an application of our axioms. So I guess the first one follows by eagerness and monotonicity. The second one follows just by eagerness. The third one follows almost directly by relevance. And the fourth one, if you're playing this back later and can look at it more slowly, is just implicit in the definition of P, because the U's are P's, the probabilities is 0 beyond the cap time. And what that means is that my utility function can look like any of these green things. It can't look like any of the red things. So it's fine for my utility function to be a step function right at kappa. It's fine for my utility function to decrease and then discontinuously fall at kappa. It's fine for my utility function to asymptotically approach kappa, remaining positive until kappa, and then going to 0 at kappa. So you can't quite see that in the picture, but that's what's happening. And it's fine for my utility function to do all kinds of wiggling as long as it remains monotone. But it can't go up, and it can't fall to 0 before kappa. Okay, so isn't that exciting for me that we could do a bunch of math about axioms and prove the existence of a utility function? I'm sure I feel great about myself now. What does this mean for you as an algorithm designer? Let me work through some examples and tell you about how you might use this if you wanted to optimize an algorithm. So there's some free parameters that you have to think about if you want to apply this theory. Because you might really have different utilities. I can't tell you what your preferences are. I can just constrain things about your preferences. So here's one scenario you might be in. I need to find a solution to my integer program by midnight or it's going to be useless. There's a competition. I need to return the answer by exactly midnight. So I've got a step function utility that says my utility is 1 until I get to midnight and then it falls down. And I have a fixed and known cap time. It's the amount of time that remains until midnight. So my scoring function then is just going to say the best algorithm is the one most likely to finish before the cap time when I push through into the utility function. And I can use this utility function to say which algorithm is better in the scenario I gave you before. And it's going to say the thing that makes sense, that if kappa is less than 10 days, then I prefer A1 to A2. And if kappa is greater than 10 days, I'm not sure anymore because the average, it might start to change, right? It might be that in slightly more than 10 days, I guess it can't be 10 days until midnight, but anyway, you see the point that I'm making. Concrete example 2, I have strictly monotonically decreasing utility and a known cap time. So I must find a solution to my integer program by midnight, and the longer I take, the lower a score I'm going to get in the competition, or the more trouble it's going to be for my client to make use of this thing that I'm giving them at the last minute. So here U is going to be any function that meets the conditions that I described earlier, provided it's strictly monotone decreasing and not weakly monotone decreasing. Again, I have a fixed and known cap time. And here the best algorithm is going to represent a balance between finishing as often as possible and getting a high score when it does finish. So it might be I would prefer to finish actually finish at all a little bit less often if you can finish really fast versus finishing a bit more often and running almost to the cap time, depending on how quickly this the monotone decreasing function decreases to the cap time. And we'll be able to say that I like A1 better than A2 as long as my function decreases fast enough. Otherwise, maybe not. Okay, so that was the case of K being known. I told you before that it was interesting to think about Ks that weren't known. Let me now try to back that up. So I think this is particularly appealing as a way of thinking about why expected utility might decrease with time. So of course, there's nothing stopping me from having a utility like the one I just described here, where my utility really does decrease because I actually know that my score decreases as a function of time or something. But I think it's often going to be the case that I care about just solving the problem, but I'm not really sure exactly how long I have. I kind of know how long I have, but I don't, nobody knows exactly down to the clock tick how much time really they have to solve the problem. Cap times are always a bit of an approximate thing in life. And so I think this is best modeled by saying I have a step function utility, or if I want to extend this later, actually some kind of decreasing utility with time, but I have uncertainty about exactly what my cap time is. So in a concrete example here, basically this just works with the utility function that I gave you before. I just have to push through a little bit more in the math. So if I have a step function utility and some unknown cap time, then the best algorithm is the one that's, again, like in example 1, most likely to finish before the cap time, but now taking expectations over cap times rather than taking expectations only over the algorithm's runtime. So now I'm taking expectations over 2 things. And okay, so if that's all I had to say, this wouldn't seem like it was worth being its own section, but you probably were thinking when I was speaking before that we don't really know exactly what the cap time distribution is. Like nobody tells me, here's your exact cap time distribution. What's the point of some theory that assumes that I know this thing that I don't really know? So here we want to appeal to the principle of maximum entropy that says, when I don't know which distribution to use among some set of alternatives, I should use the one that has greatest entropy because it's the least informative. So I want to make a set of alternatives based on some constraints that I might have in the distribution K. And then I want to use maximum entropy to say which k has maximum entropy among those distributions that satisfy the constraints, and let me treat that as my k. So for example, if I said, all I know is the distribution has support on some bounded interval, the maximum entropy recommendation would say you should think that you have the uniform distribution over that interval, because anything else would involve making some additional assumptions about the shape of the distribution. So applying that idea, if I wanted to say, my client needs a solution to their SAT problem sometime in the next 24 hours, but I'm not sure exactly when, then I recommend that we say my maximum entropy distribution is uniform, and that means that I'm going to have linear utility for time, because the expectation that my problem will actually solve under this uniform cap time distribution kind of induces these linear preferences, given the step time utility function, the stepwise utility function. But then I can do more exotic things. Uniform is pretty, but there's lots of other sorts of assumptions that I can make that would induce different cap time distributions, and even cap time distributions with infinite support. So maybe I know the mean. I don't know how long the client is going to give me to solve their SAT problem, but I think the mean of the cap time distribution is going to be 24 hours. So in that case, the maximum entropy distribution is an exponential, and that induces this utility function that I'm showing here. Or maybe I know the expected order of magnitude of the cap time distribution. So what if I said the client is definitely going to give me at least 1 day, and the amount of time they give me is going to be on the order of d days. So in other words, the expected value of the log cap time is going to be log d. In that case, the maximum entropy distribution is Pareto with this shape parameter given here. So my PDF says, for sure, you've got at least 1 day, and then you've got a Pareto distribution. And I can do various other things. So if I can build up stepwise constant stepwise uniform PDFs. If I say my cap time is less than some number with certainty and then less with some other number with some probability, I can justify the log normal distribution. If I know a mean, a log mean and a variance, I can justify the log Laplace distribution or the generalized log Laplace distribution. So there are various assumptions that I could make about what do I think I know about how long I would have my algorithm to run, and those would induce different distributions over the cap time distribution, which then can be combined with my utility function, which in this case, just for analytic simplicity, I'm always making be stepwise, but it doesn't have to be stepwise. It can be anything. And then you can evaluate this expectation. You can score your runtimes. So let me give you one last concrete example of what that looks like. So if my client is going to give me at least 1 day, and the expected order of magnitude of the cap time is 2 days, then I have this Pareto case. So I have this function here, and I could use this to plug into my 2 algorithms, say which algorithm is better. I can score the 2 algorithms, and I can get bounds on how big the score can possibly be given these caps. And I can say algorithm A1 is at least 10 times better than algorithm A2. So there we go. I think we're just on time. So in conclusion, there's a bit of a whirlwind, but I hope you took the main points that it's surprisingly non-trivial to formalize why I prefer one runtime distribution to another, particularly in the presence of capping. And what we tend to do in practice is either to make unjustified assumptions like knowing exactly what the cap time is and then taking averages over that interval, or to say things like I prefer the average runtime and not really being able to justify why I am so motivated by this dominant possibility of tail events. And this is really, it might seem like a bit of a curiosity, which I think is why this paper has never been written before. But as we move to learning special purpose algorithms, where I'm not really looking at them and seeing whether I like the recommendation that I'm making, but I have some machine learning algorithm that's just optimizing over these scores in a black box kind of way, it might behave in a bit of a perverse way if we don't get this objective function right. So this paper presents a utility theoretic answer to this question based on making axiomatic assumptions about preferences over runtime distributions. And the key sort of parameters that it leaves open to you is the way that utility decreases over time. And in most of my examples, I talked about step functions where you don't care about time except at the cap time you fall to 0. but I said that you could also have various monotone decreasing functions if you know something about your domain. And it also depends on the cap time distribution. And I gave you the intuition that even if you have the step function domain, you can kind of see that as a story about why your expected utility decreases over time. And I also talked about the world where you don't really know the cap time distribution, but you know some property about it, like an order of magnitude. And I showed how we can use the principle of maximum entropy to come up with cap time distributions that would be appropriate to use under those various assumptions. So I'm excited about what this work might mean for approaches like algorithm configuration. I don't think anyone has ever run an algorithm configuration procedure with an objective function like this, and I literally don't know what it would find if you ran it for a SAT solver. I think you might find really interesting algorithms that actually have performance that looks more appropriate for what we really care about than these weird kind of par sorts of things, or just a fraction of solving sorts of things that we've used in our own work in the past. And I'm also really interested in how we can use this for theory. So I'm interested in deriving lower bounds on the runtime cost for essentially the statistical test of saying, I like A1 better than A2. So notice that everything that I did in the work today presumed that the runtime distribution of A1 and A2 are known, and that it's just a matter of just even figuring out, do I like A1 better than A2? But of course, in real life, I never know two runtime distributions. Instead, I sample from A1 and A2 to get sort of estimates of their runtime distributions. And this leaves open the question, what's the cheapest way of making observations about A1 and A2 in order to establish that I like A1 better than A2 for different utility functions? And the reason that's tricky to do is that I can do this sampling with cap times. So I can say, really, my cap time is a day, but let me do a whole lot of runs only up to a second, because they're really cheap to do. And I can learn about, I know my utility function really cares about how much I can get done in a second. So I can play this game of being strategic about how to do the capping in order to make these statistical tests cheap, not in the sense of involving few samples, but involving a few kind of amortized samples where I amortize them by the cost of the samples. And lastly, we're also interested in extending our utility functions to include solution quality. So I'll leave it there. Thank you for your patience. Thank you for sticking with this workshop all day. And I'm happy to take your questions.
Thank you, Kevin. It was a wonderful talk and really novel and fresh perspective on this aspect. So there's some time for questions. If you have any question, you can either raise your hands or unmute yourself and ask a question directly.
So Nando, there is one in the chat already.
So Jean is asking, can you say something more about extending this to a situation where speed is not the only criteria?
Yeah, so that's actually the last bullet in my future work points here. So that's something we're kind of thinking about. Sort of, you're not going to get something for nothing here, right? You're eventually going to have to, one way or another, tell me how you feel about different solution qualities, right? So effectively, you're going to have another term in the utility function that says how do I feel about lotteries between a little bit less solution quality but faster runtimes? And there's, the user is going to need, in one sense or another, to trade off those two things. Mathematically, it's not really hard to make that go through. If you can supply that trade-off function, you can just basically put it into the utility function along with everything else and take expectations. It's going to go through in the same way. What we're thinking about is how best to axiomatize this so that we can kind of do as much of the lifting for you about what that function would be. So I think everything that I said here is a problem, even in the case where solution quality is not a problem. So it seemed to us that the right thing to do is just to get this machinery working before the added complexity of adding in solution quality. But it's not going to be an inconsistency for the theory. It's just going to be kind of an extra dimension that gets layered on top.
Any other question?
I have two questions, and I think you already answered one of them in the last one. First of all, thanks a lot for the great talk. I mean, as usual. So I wanted to ask you about like anytime algorithms, and can they also be, reasoned about in this framework? So I think that falls into the solution quality argument that you alluded to before. And the other question was, about some kind of a adaptability for you. So can you become more adaptable as we move along, as we execute the algorithms? Can we incorporate some of the information? Maybe you also pointed that out during your talk and I missed it, but can we incorporate some of that information? So for example, I've executed this algorithm up to this particular point, but I haven't reached the timeout yet. So that's a piece of information that I can incorporate into my decision-making about perhaps choosing between the algorithms from that point on, or something like that.
Yeah, so I think, so on your first question, yes, I think that's exactly a question about solution quality. On your second question, no, you can't, but I think what you're really asking about is the first bullet of related work. So let me, of ongoing work. So let me try to explain. If I've done a partial run, my preferences for all the counterfactual things that could happen in the world aren't affected by the partial run, right? The utility function says, how would I feel about the runtime being whatever, whatever various set of things that it might be? And that's kind of my objective function, right? My objective function isn't changed by having new information. What is changed is my belief about what objective function what specific objective function value I might actually end up getting, right? So it isn't that the function itself is going to change, right? U is going to be whatever it is. That's a fact about you, that like you personally, that says, your client is really not going to give you more than 24 hours. If you've run for half a day, you don't start to think your client's going to give you more time. That's just whatever it is. I mean, you can renormalize the distribution and say, like, now my posterior belief conditional on what I've already observed is something else, but that doesn't change the ex ante story. But what you can say is, if I'm trying to decide whether A1 is better than A2, then, and I've done some initial runs with A1, maybe only up to certain like runtimes. I've characterized, with some sample, like some early part of the CDF of A1's runtime, that's giving me some posterior belief about what else I would need to learn to decide whether A1 was better than A2. So that isn't a thing about my utility function. That's a thing about how I can most efficiently go about gathering additional information to certify to myself that A1's better than A2. So that's really a story about sampling. And I agree with you, that's fascinating. I think there's a lot of really deep work that I think you can come up with some really elegant ideas about how to leverage that. And it's going to depend on the shape of the utility function. But because the utility function is always going to be some decreasing thing, there's something really beautiful, which is that I get the most utility from the shortest runs, right? So the thing that is the cheapest to learn about is also the best for my utility. And that gives me this world where I can do lots of very cheap capped runs and potentially learn a lot about the most valuable part of my utility function. And that's why I'm really excited about this sampling direction. I think it's going to, the structural procrastination work, if you know it, is a really disappointing kind of sampling story. It says, when I've got an algorithm that looks amazing, I have to do lots of long runs to make sure that there isn't some vanishingly small probability of a really enormous run that blows up the average and becomes a fly in the ointment. So all the time, what you're doing is going and looking for things you've never seen before that take forever, that might make it look worse than it really is, even when they never occur. Right? This kind of world is going to let me say, I want to look for unlikely good things that might raise my utility rather than looking for unlikely bad things that actually never happen. And I think that looks much more like what we really do in practice.
Maybe there is a time for just another quick question. We're a few minutes out of time, but.
If I can cheat and ask one. Kevin, are there any implications for how people should report results in papers on new algorithms, whether they are including any learning component or just any algorithmic enhancements? Because I've noticed that in the SAT community, the PAR K 2 or 10 are kind of frequently used, but they have this bias issue that you denote that their dependence on a particular cap. Whereas, for example, in integer programming, people tend to do geometric means on running times, and also maybe count. At least something I do is I also count the number of solved instances, and sometimes people do performance profiles. And in combination, those three seem to give enough information to kind of, compute any kind of, depending on what your utility is, you might take these results from a paper and decide, oh, I actually don't prefer your new algorithm. The older one is better. So do you have any insights into that? Like, how should people report their results in function of what you have?
Yeah, I mean, I think that's a great question. I think it's kind of early days. As I say, we haven't even put this paper on archive yet. So, give us some time to get our ducks in a row here. But I do hope eventually that this line of work, as the community weighs in and responds, will eventually get us to a point where we can have a much more principled way of doing that sort of thing. I'll say I once had a collaboration with some people at CPLEX, and they kind of introduced me to this geometric mean sort of approach. And the way they explained it to me was to say, we're shipping this tool that our downstream people are going to use. And I don't know if they're going to have a minute to do the run or a second or a day. And I want it to kind of have good performance in all of these different scenarios. I think that kind of planted the seed for me in this sort of uncertainty over cap time point, right? That the sort of geometric mean viewpoint, I think, encodes within it the idea that you're building a tool for a downstream user whose cap time load might be very different. And you want somehow to sensibly trade off these different scenarios. So I think there's probably a way of using this kind of theory as a sort of more more justified explanation for why these are the measures that we use. I think other times you really know your cap time, and then the step function with a known cap time and just saying what's the solve percentage, it just really seems like the right thing. If I'm Amazon and I want to send the trucks out in exactly 10 minutes and do the best thing you can with the vehicle routing, and then the trucks are going to go. I don't care about saving 1 minute and getting the answer in 9 minutes. Just do something in 10 minutes and then off we go. There are lots of cases that really look like that too. So I think one real takeaway for me here is that there isn't one utility to rule them all. It isn't like everything should be geometric mean, because there just really are cases where your preferences are going to be different. But I think what I think doing this work has persuaded me is that in a paper we should be explicit about what utility function we had and what our claim is derived from. I think you can sensibly justify a wide variety of different utility functions, and that's cool. I think you can tell people why. I think those utility functions should be bounded, right? So I think we shouldn't have crazy tail events that become arbitrarily important to our utility function kind of without limit. That's one result of this analysis that says that's why this average thing was really kind of wrong-headed. So I think that's a concrete claim that we shouldn't do theory work where arbitrarily unboundedly large runtimes with arbitrarily unboundedly small probabilities can dominate our analysis. That really shouldn't be allowed to survive. Almost anything else can survive. Anything on a bounded interval can survive, but we can be explicit about which assumptions we made and why it is that we optimized the function that we did. And really my hope is, for all that this was like a lot of math and a lot of squiggly greater than symbols, at the end of the day, this is going to let us run, figure out, okay, my utility function looks more or less like this. Here's my loss function. Let me run, SMAC or, my algorithm configurator of choice with that as given as the loss function. And it's going to find something surprisingly better that will be better than par. And really will just give me a solution that I'll like better. That's really why I'm excited about this work.
Yeah, I guess as long as the utility is kind of additive or separable, etc., that kind of amenable to some kind of average case type, though, right?
Well, notice all the utilities talk about expectations. It's always going to be expectations over these individual points. So they're always going to be approximable from samples because you're averaging something. So that really always is going to work out, right? The Norman Morgenstern style result, it really has two pieces, right? It says there's a utility function. It also says what you care about in the case of randomness is expectations of the utility function. Attitude towards risk is not some other thing where I care about quantiles or medians or something. I really care about expected values. So really, it's those two things together.
Nice. Thank you very much.
Cool. Thanks again for the opportunity to foolishly try to present this half-baked work to all of you.
Let's thank Kevin one more time. And yes, thanks for the wonderful talk.